Our next thing to learn to differentiate is something called parametric equations. Now, this is not necessarily a formal definition of what a parametric equation is. I will give that afterwards, but this is how I like to think of it first. Say that we had a car and it was going around a corner that just happened to model y equals square root of x. So this is the corner that it is turning around, following y equals square root of x. Now you could track the position of the car. Let's just pretend that this red part is the car. It's going that way. You could track the position of this car by seeing its coordinate at any point and seeing how it follows. So almost like a bird's eye view. Now another way to track the position of the car is, instead of basing it off its coordinate, is to base it off a time variable, because we know the car is moving in time, and so we could track its x location and its y location based on its time. Now this time is a third variable, and parametric equations formally is where you introduce a third variable that allows you to track y and x almost independently. So in this case, we can track the car through the equations y equals t and x equals t squared. Now you will not be expected in differentiation to get these equations, but just showing that this does work, well, since y is equal to t, we could substitute that into our x equation to get x equals y squared. Square root both sides, you get y equals plus or minus the square root of x. And since this is just the positive part of it, we can get y equals the square root of x. Now since both x and y are in terms of t, that means that when we differentiate y, we're going to get dy dt. And when we differentiate x, we're going to get dx dt. Let's do that for this example. We have y equals t. So therefore, dy dt is equal to 1, and x equals t squared. Differentiating x in terms of t, we get dx dt equals 2t. Now neither of these are dy dx, so if we wanted to calculate the gradient of the tangent along this line, i.e. sort of the direction that the car is facing at any moment, we need to get dy dx. To get dy dx, we're going to follow an equation, but really it's just an application of fractions. Now dy dx, I'm going to split this into its dy over something times by something over dx. Now if the parts of the fraction that are missing are filled by the same term, then they will cancel and we'll get dy dx. In our case, we have dt in both. Now, how do I get dt dx? Because I've only got dx dt. Well, I can simply take the inverse, which means dt dx, in this case, is 1 over 2t. And therefore, dy dx will be dy dt, which is 1 times dt dx, 1 over 2t. We get 1 over 2t as our answer. So, say we had the parametric equations, x equals 3 cos theta and y equals 4 sine theta, and we wanted to calculate dy dx at theta equals pi over 4. Now there's no t variable on this, but it's just theta, it's just another letter. That means that because it's theta, we now change our equation to dy dx equals dy d theta times d theta dx. So to get dy d theta, we differentiate our y equation. Sine differentiates to cos, and so we get dy d theta equals 4 cos theta. Now since the function inside of the cos, i.e. the theta, differentiates to just 1, we don't need to times by anything, in effect we are timesing by 1, which is still an application of the chain rule. To get d theta dx, it is a lot easier to first get dx d theta and then take the reciprocal, as opposed to rearranging our x equation for theta first. So dx d theta equals cos differentiates the negative sign, so negative 3 sine theta, which means that d theta dx is equal to 1 over negative 3 sine theta. And typically we write a negative on the top of the fraction, so that's negative 1 over 3 sine theta. Substituting these two into our parametric equation, we get dy dx equals 4 cos theta times negative 1 over 3 sine theta. That simplifies to negative 4 cos theta over 3 sine theta. We can simplify that, but we don't need to, because we can now substitute theta equals pi over 4 straight into this equation. Dy dx equals negative 4 cos pi over 4 all over 3 sine pi over 4. Of course, making sure that your calculator is in radians when you're calculating this. That will give you an answer of negative 4 over 3. So that is essentially the application of the first derivative for parametrics. And it doesn't really change that much more than that. Of course, the functions might be slightly more difficult to differentiate, but you have the skills from previous taught functions. The parametric second derivative is a little bit more involved, but if you get used to how you answer the questions, there should be no surprises. So, parametric second derivative. For example, in a simple case, x equals 4t squared, y equals 8t. And we want to find the second derivative. Well, to find the second derivative, you first have to find the first derivative. We'll do that. dx dt equals 8t, and dy dt equals 8. That means that dt dx equals 1 over 8t, and then dy dx equals dy dt, 8 times 1 over 8t, which is 1 over t. Now to get the second derivative, we have to be very, very careful. We can only differentiate this dy dx equation in terms of the function t, which means when we differentiate this, we're not going to get the second derivative. We're actually going to get differentiating in terms of t of dy dx. Now we want d squared y over dx squared. Now it's worth noting that this form is actually slightly lazy if we consider that d and x are separate variables. It really should be written with brackets, but you could also consider that dx in itself is just one variable, and so therefore it doesn't technically need it. Currently, this is equal to d squared y over dt dx. We need to get rid of the dt on the bottom and add a dx to the bottom. To do that, we need to take our fraction and times, we need to get rid of the dt on the bottom, which means we need to times by dt on the top, and add another dx to the bottom. That there will then cancel, and we get what we want. That gives us our second derivative parametric equation of the second derivative is equal to d dt of dy dx which just means differentiate the first derivative equation in terms of t, which since the first derivative equation is in terms of t already, that will just be a normal differentiation, and then times by dt dx afterwards. In our case, we know that dy dx is equal to 1 over t, and since we have to differentiate this, I'm going to rewrite this as t to the power of negative 1. So that means the second derivative is equal to differentiate the first derivative, negative in front, reduce the power by 1, and then times by dt dx. Well, dt dx from previously was 1 over 8t, so times by 1 over 8t. Simplifying, we get negative 1 over t squared times 1 over 8t, which is negative 1 over 8t to the power 3. So the actual differentiation in terms of our second derivative is not that hard. You just have to remember to times by dt dx afterwards. Okay, another example. X equals 3 sec theta, y equals 4 tan theta. And we want to calculate the second derivative. Dx d theta, differentiating first. Sec differentiates to sec theta times tan theta. So this is 3 sec theta tan theta. And dy d theta, tan differentiates to sec squared, so this is 4 sec squared theta. D theta dx will then be 1 over 3 sec theta tan theta, and so dy dx is equal to 4 sec squared theta times 1 over 3 sec theta tan theta. One of those secs will cancel with one of these, and we get equals 4 sec theta over 3 tan theta. Now this will require a quotient rule to differentiate, but because they're trig functions, I might just see if this can simplify down a little bit more. We could rewrite this as 4/3 times sec theta times 1 over tan theta, which if we were to rewrite these in terms of just sine or cos, is 4/3 times 1 over cos theta times cos theta over sine theta. Those causes cancel, and we get 4 over 3 times 1 over sine theta, and 1 over sine theta is cosec theta, so we get 4 cosec theta over 3. That is a lot easier to differentiate because there is a rule for differentiating cosec theta. To get the second derivative, we will then differentiate this first derivative in terms of theta. Cosec differentiates to negative cosec times cot, so you get negative 4 cosec theta cot theta over 3 times by d theta dx, or 1 over 3 sec theta tan theta, 1 over 3 sec theta tan theta. Now that's quite messy, but again these are trig functions, so we can rewrite them in terms of sine and cos. Now in terms of our coefficients, we've got negative 4 on the top and then 3 times 3 on the bottom. That's negative 4/9 times cosec times cot. Well, cosec is 1 over sine theta. Cot is cos theta over sine theta times, with 1 over sec theta tan theta. Well, 1 over sec theta is just cos theta, and 1 over tan theta is cos theta over sine theta. Nothing here will cancel, but we can simplify because we have 3 coses on the top, cos cubed theta, and 3 sines on the bottom, sine cubed theta, which gives us negative 4/9. Cos over sine is equal to cot, so negative 4/9 times cot cubed theta. Now, of course, this is the most simplistic way to write this, but you don't have to always simplify to get an answer out correctly. We have 4 past exam questions involving parametric equations. They're a mixture of first and second derivative. First exam question, you're given x equals 2 plus 3t, y equals 3t minus ln of 3t minus 1, and you are told that t is always greater than 1/3. Now that domain on t is only there because if t is equal to 1/3 or less than that, you get ln of 0 or ln of a negative number, which does not work. Now sometimes you will get multiple values of t at the end, and you can also use that to help you maybe eliminate one of them. You're asked to find the coordinates where the tangent to the curve has a gradient of 1/2. Now when it says coordinates, it means an x value and a y value, not just a t value. So tangent to the curve means dy dx, so dx dt is equal to 3, which means dt over dx is equal to 1/3. dy dt is equal to 3 minus ln differentiates to 1 over, and then times by the derivative of the bracket. Now please be careful that timesing by 3 is only applied to that fraction, it's not applied to the 3 before the fraction. That then gives you dy dx equals 3 minus 3 over 3t minus 1 times by 1/3, which if you expand that 1/3 into it, we're going to get 1 minus 1 over 3t minus 1. Now solving for when the gradient is 1/2, 1/2 equals 1 minus 1 over 3t minus 1. Well, I'm going to bring that negative fraction to the left hand side by adding it, and then the half to the right hand side by subtracting the half. The point of that is just to get rid of the negatives. I then get 1 over 3t minus 1 equals 1/2. To solve, cross multiply, 2 equals 3t minus 1, add 1, 3 equals 3t, divide by 3, t equals 1. Now it did ask for the coordinate, so t equals 1 is not a coordinate. Coordinate does mean x and y. So my x value when t is 1 is 2 plus 3 times 1, or 5, and my y value when t is 1 is 3 times 1 minus ln of 3 times 1 minus 1, which gives me 3 minus ln of 2. You can write this as a decimal, but you don't have to, and there's no need to, which means the final coordinate will be 5, 3 minus ln 2. Question 2. You are given the parametric equations x equals 4 cos theta, y equals 4 sine theta. You're actually given a picture for this as well. Looks like this. And you're told that these parametric equations represent a circle and on the circle there is a point PQ which has a tangent there. We are asked to show that the equation of the tangent line is equal to px plus qy equals p squared plus q squared. Now it is sort of telling us what to do, it's telling us we need to get the equation of a tangent, which means we need to differentiate, find a gradient, sub in a point, and rewrite that for the equation of our tangent. So, gradient, dx d theta equal to negative 4 sine theta, and dy d theta is equal to 4 cos theta. That means that d theta dx is 1 over negative 4 sine theta. Getting dy dx, we're going to do 4 cos theta times by 1 over negative 4 sine theta, which gives us 4 cos theta over negative 4 sine theta. Now, it may be tempting to cancel the 4's, and it's okay if you do, but it does make this question slightly more complicated. Because at this point here, to find an equation of a gradient, we'd normally sub in an angle, theta, but we're not told anything about an angle, and there's no real way to get that angle either, which means there must be another trick here. And the trick here is to recognize that x is equal to 4 cos theta, and y is equal to 4 sine theta. And those two things appear in our numerator and denominator, which means we can actually substitute dy dx is equal to 4 cos theta, which is x, over negative 4 sine theta, which will be negative y. Now that's a bit better because we're actually told a point. We're told that x1 is equal to p and y1 is equal to q, which means my gradient of the tangent will be, well, x is p and y is q. So there's my gradient. To get the equation of our straight line, we'll follow the rule y minus y1 equals mx minus x1 and substitute everything that we have in. Y minus q equals p over negative q times x minus p. Looking back at the form that the answer is in, it's all in a fairly more expanded and simplified form. So let's times by that negative q to get rid of it from our denominator, giving us negative qy plus q squared equals p x minus p. And expand that bracket, we get negative qy plus q squared equals px minus p squared. To get it into the form that the question wants it, well, it's got everything positive, so let's just move the negatives to the other sides. We get p squared plus q squared equals px plus qy, which is the form that the question wanted it, albeit the question had it around the other side of the equal sign. Therefore, px plus qy is equal to p squared plus q squared. Now, if there's a second derivative question, it's typically always going to be an excellence question in NCEA. So say you got x equals ln of t, y equals 6t to the power 3, and you're told that t is greater than 0. We're told that p lies on the curve, and at p, the second derivative is equal to 2. Now this is telling you exactly what to do. It's telling you to get the second derivative, make it equal to 2. And then the question actually asks to find the coordinates of p. So once we have the t value at the second derivative, we can then substitute that back into our x and y equations. Seems fairly straightforward. Dx dt is equal to 1 over t, which means dt dx is equal to t, the reciprocal of that fraction. Dy dt is equal to 18t to the power 2, which means that dy dx is equal to 18t squared times t, or 18t cubed. Then our second derivative Well, that's equal to the first derivative differentiated, or 18 times 3 is 54, t to the power 2, and then I'm going to times by dt dx, which is t. The most common mistake is to forget to times by dt dx. That gives us 54 t to the power 3, and we're told that this is equal to 2. So, divide by 54, we get 1/27th is equal to t cubed, and take the cube root of the fraction. That gives us 1/3 equals t. Quick check, we're told that t must be greater than 0. This is, so we're okay. Now all I need to do is find the coordinate, so that is subbing into our x and y equations. So x equals ln of 1/3, and y equals 6 times 1/3 to the power 3, which gives you 2/9. So your answer could be ln of 1/3, 2/9, or if you're feeling like you wanted to do a little bit more work on the ln of 1/3 could be rewritten as ln of 3 to the power -1, and since we have a log rule which says you can bring a power in front, that gives negative ln of 3. So an alternative answer would be negative ln 3, 2/9. Both are equivalent. You could also give a decimal value for ln 3, unless the question asks for it in exact form, in which you could not then do that. One more example. Previous exam question, which says that a curve is defined parametrically by x equals 3t squared plus 6t plus 1, and y equals 2t to the power 3. The question is, find the coordinates of any point of inflection on this curve that are also stationary points. Now you are also told in this question that you may assume that any inflection points found are actually inflection points. And the reason it says this is that sometimes when you get the gradient is equal to 0 and the second derivative is equal to 0, you sometimes can get points of inflection, but you can also sometimes get maximums or minimums. And so that sentence there is purely just to tell you that it is a point of inflection. You don't have to do any other tests to confirm. Reading this question carefully is very important to get the full marks for this question. The way it's written, because point of inflection is first, it's implying you need to calculate the second derivative, make it equal to 0 and solve that, and then sub those values of t into your first derivative to show which one is a stationary point. If you found the stationary points and then substituted those into your second derivative, unfortunately you weren't actually able to be awarded the full marks. So just be very careful with the order that the sentence is written in. So to get our points of inflection, we need to get the second derivative. dx dt is equal to 6t plus 6, which means dt dx is equal to 1 over 6t plus 6, and dy dt is equal to 6t squared. That means that dy dx is equal to 6t squared times 1 over 6t plus 6. Now all those 6's will cancel, and we get t squared over t plus 1. That's our first derivative equation. We need the second derivative for points of inflection. So do that. We get, it is a quotient, so we need to use a quotient rule, which says differentiate the top times by the bottom minus the top times by the derivative of the bottom, all over the bottom squared, and then times by dt dx again, 1 over 6t plus 6. Now, expanding and simplifying the top, we get 2t squared plus 2t minus t squared, all over t plus 1 squared times 6 lots of t plus 1. If you were to factorize the denominator, that gives you t squared minus 2t all over 6t plus 1 to the power 3. Now you don't actually have to simplify and factorize the denominator, but you can, but it won't help. Because for a point of inflection, we need to make this equal to 0. The only way for a fraction to be equal to 0 is if the numerator is equal to 0, which means that t squared minus 2t is equal to 0. So all that work on the bottom, on the denominator, wasn't really worth it. Solving this, we can factorize t out. We get t times t minus 2 is equal to 0, and so t equals 0 or t equals 2. Now that we have two values of t, we're going to go back to our first derivative and test which one of those gives a stationary point, i.e. a derivative of 0. So at t equals 0, dy dx equals 0 squared over 0 plus 1, which is 0, so that one works. And at t equals 2, dy dx equals 2 squared over 2 plus 1, which is 4/3. That is not a stationary point. So find the coordinates of any point of inflection on this curve that are also stationary point. We know that t equals 0 is the only value that this works for, so we can substitute that back into our original x and y equations to get the coordinate. That means that x equals 3 times 0 squared plus 6 times 0 plus 1, which is just 1, and y equals 2 times 0 to the power 3, which is 0. So our final answer is 1, 0.